Okay, so the presentation has been done. I'm going to talk about memory. I'm going to talk about how the hardware handle memory and what is the memory what is the like all languages handle memory and what are the semantics you can adopt to manage memory. So first of all, this is the von Neumann architecture. This is pretty much what every computer looks like right now. If you look like from far enough. Yeah, well, most computers right now are a bit more complicated than that, but like the general idea is still there, right? You have the ALU that does the work. You have the control flow unit that decide what works need to be done, and this is in the CPU, and this communicate with some memory to store and recover information to have a bit more state. So the thing is, memory is super slow, and by slow I mean you need about 300 cycles to hit memory on a typical modern machine. That is really slow. As Walter mentioned, this is like 100 times slower than to hit some hot cache, for instance. Bandwidth is still increasing to some extent. So when I say slow, you're going to understand it as slow, like it takes time, and not as how much data you can transmit over the wire. This is still a limited resources, but this is not even, this is not closely limited as the latency is. And yeah, latency is like completely marginally increasing. There have been no progress made in latency, like only marginal progress made in latency over maybe at least the past 10 years or something. Like we just stopped making significant progress on that. And the problem is that the rest of the computer have grown in terms of speed and resources and everything exponentially. So the gap has become really big between memory and the rest of the machine. So the obvious solution is to add some extra memory on the CPU, and so that memory can act as a cache. And it's way smaller than the main memory, but you can store some information in there and go fetch it and write it there instead of going to memory for the data that you use the most. So there is some number in there. Typically, you have several levels of cache, and the first level is like very small and very fast, and as you go toward the level, they become bigger and slower. There is a physical reason for that. It's just the signal need times to travel across the chip. So it may seem like an electric signal traversing a microchip would be actually very fast, but CPU are really fast. Like we are working at nanosecond time scale, and this actually takes a significant amount of time. So most of the data you have in there are obviously depending on the CPU. One that is pretty much constant is the L1, which is pretty much always 32 kilobytes right now and always 3-4 cycle on pretty much any machine. And this is because we are hitting our physical limits on that one. If you would make it bigger, it would be like twice as slow, and this is completely unacceptable for L1. And if you make it slower, then you cannot do much with it, and you have like some extra cost, so you wouldn't be able to make it much faster. So there is a nice trick we have found. Well, not we, but the hardware people, they have found, is to actually put two L1, one for the data and one for the instruction. And as you have like in the von Neumann different unit that access those two, you can have like two paths to two different caches. So this is roughly what it looks like. You have the L1 for instruction that talk with the control flow unit. It goes only one direction, right? The control flow unit is not supposed to write instruction in memory. And the ALU can talk like bidirectionally with the L1, with its own L1. And both are 32 kilobytes. They are physically separated, and like there is literally two different hardware paths to access the two. There are like two different physical units. So Another thing you can do is try to prefetch, and CPU know how they do that. Basically, the CPU is trying to predict what memory you're going to access next. And it tries to load that memory before you access it, so it's out in cache when you actually want it. Basically, it's trading memory bandwidth for hope that you will access this, this memory. Usually it's pretty good. It obviously depends a lot on your memory access pattern, right? So if you access the element of an array in order, that's very easy for the CPU to see what you're doing and prefetch the stuff. If you are like traversing a graph of pointer or stuff you have allocated on heap with malloc, then the prefetcher cannot do anything for you. So here is like some good practice you can adopt in your code, so it play nice with the way memory works. So the first thing you want to do is like put as much stuff on the stack as possible. The stack is hot pretty much always. And so it's always like in your L1 cache, worst case scenario, L2 cache if you returns a lot or call a lot and it's deep down. But generally it's pretty hot, so put your data there. That's a good place. Pack your data. So if you have like some bits left here and there, you can put a lot of stuff in one bit. Like, one bit can be a mutex, for instance, or one bit can be like whatever, a flag to indicate something. You can do a lot with one bit. So if you have like some bits around that are unused, just put some stuff in there. Basically, your memory footprint is lower, so you can fit more in cache, and you have more. So you have more of your data set in the cache. You got to avoid indirection, simply because because of the hardware cannot prefetch indirection. It doesn't know what you're going to load. And actually, it's the same thing for the optimizer of the compiler. So basically, like indirection make both the hardware and the optimizer of the compiler completely blind. And you don't really want that. So like indirection are unavoidable, right? But avoid to do the Java thing where you have like an indirection to your vector plus an indirection to the storage of the vector that store only pointer to object, so that's an extra indirection, right? So if you access an element in the vector in Java, you have 4 indirection to go through, and that's really bad. In diff, you use a slice, for instance, and your element are struct instead of some reference type, then you only have 1 direction to reach them. That's much better. So generally limit indirection. Try to access element in a linear fashion so the prefetcher can play nice with you. Sometimes it's worthwhile to sort elements before working with them, or at least pseudo-sort them. Benchmark, it may depend on your application, but generally you want to access stuff in order if that's possible, or at least in pseudo order. And try to size the data structure you use in your program. So I have 2 examples here. You may know those are 2 compression algorithms, LZ4 and ZSTD. Those are 2 compression algorithms and decompression that are known to be very, very, very fast. And one of the things they do is that all the data structure they use is 16 kilobytes. So it's half of the L1 cache. So you have like the other half of the L1 cache to have a part of your stack and some of the data you're working on that come from the input stream you are trying to compress or to decompress. And then you have like half of this cache that is some data structure used by the algorithm itself. And 16 kilobytes is usually, the kind of size you want to aim for your data structure of your algorithm. But that's not it. We have the MMU. So the MMU is like the memory unit of the CPU. It does a lot of stuff. It does everything that I explained before, but it does also memory protection. It does translation from physical address to virtual address and the other way around. And this is important because you want your application to manipulate virtual addresses only for security reason, for various features you want from your OS. So for instance, the OS can, if you don't have enough memory, swap some of the memory to the disk. And so from your program perspective, there is still some memory there, but there is no physical memory there. and then we try to access it, the OS, it's going to trap into the OS, and the OS is going to reload it. Or you want some feature like fork, where you duplicate a program, and then, like the two sample code will access the same addresses in memory, but you want them to eat actually different physical memory, at least when they write. So that's fairly important for security reasons as well. You don't want to execute random data in memory. You don't want to write into read-only section of memory of that. So the MMU is going to handle it. And it's going to handle it by pages in memory. Usually a page is 4 kilobytes. It depends on CPU, right? And there is usually several modes you can use your CPU in. Some, like x86 allow 2 megabyte pages as well, for instance. But like 4 kilobyte is the standard, is what you will see most of the time. And so on those 4 kilobytes, you have a translation from a virtual block of memory to a physical block of memory, and you have the protection associated with that block. And the information about those blocks are cached in what is called a TLB, translation look-aside buffer. And you usually have 16 entries in the first level of cache of the TLB, and then you have several levels of them. The TLB must be really, really fast because the TLB check must be done in the 3 or 4 cycle where you hit the L1 and the data come back. You need to go through the TLB as well. So roughly, here is how it works for a 4 kilobyte page. You basically have your lower bit of your address. The 12 lower bits of your address are the same between the virtual and physical memory, because your pages are 4 kilobytes. So this is basically 16-bit. This is what you can address in a 4 kilobyte chunk. And those are the same bits between the physical and the virtual address. So you have like all that come before that goes to the TLB, and the TLB is going to try to find what page is that, and what is the physical address of that page, and do I have the authorization to do the operation I want to make? Like, do I have the authorization to execute? Do I have the authorization to read or to write? So the higher bit go to the TLB, and if you have a cache line of 64 bytes, which is the usual size, then you have like 6 bytes that basically indicate what is your offset within the cache line. And the other 6 bits are basically what you can use as a key in the L1 cache to do your lookup in the cache. And by doing this as a key in the L1 cache, you can do the lookup in the TLB and the L1 cache in parallel. And then you aggregate the result. And then using the 6 smaller bits, then you can find where you are in the cache line and get the actual value you're interested in. So that is a nice trick that the hardware people use to be able to have some parallelism in the TLB. Because otherwise you would have to do like the TLB lookup, find the physical address, and then go to the cache. And that works for higher level of cache, but that doesn't really work for L1 where you want it to be super fast. This doesn't work for bigger caches, obviously, because you have only 6 bits for the key. So if your cache get significantly big, then you're screwed. Another thing, CPU have all gone multi-core. So you probably have one of those devices as well. There is 8 core in that, and this is like 2 years old. This is absolutely ridiculous. We have like so many core in any chip right now. And we have some problem with that with memory, right? Because we have many cores that execute many stuff, but you have only one main memory, right? So there is some collision in there. So multi-core, basically it's everywhere. Server, desktop, laptop. I could add in your phone and probably in your microwave in your car. So yeah. So why did we went multi-core? We went multi-core because basically the single core stuff, we had smaller and smaller return by improving the single core CPU. So you get your transistor smaller and smaller and smaller and smaller. You can put more and more stuff on your chip, and you don't know what to put in there. So the easy, obvious solution is like, let's put more core in there. And so we can do more stuff in the chip. So that's basically where the hardware people, find themselves, and this is what they did. It causes a lot of problem for us programmer. Yeah, so this is what I explained. So unlike previous improvement, this is very visible to the programmer. This is not like, previous improvement in CPU, you had like pipelining and branch prediction and prefetching, caching, and all of that. And all of that works, your program just executes the same way, just faster. But for the multi-core stuff, it's actually very visible for the programmer, and it can be very dangerous to the programmer if not done properly. So you're required to adapt your program. And there is a lot of stuff that are very non-obvious, and basically your sanity is in danger. If you have tried to debug some race condition, that's one of the worst bugs you can have. Yeah, race conditions are the worst, right? And they are usually very difficult to repro because they will happen, one time in 1 million, for instance. So you have very hard time to have a test case that is going to reproduce the stuff consistently. But considering how fast modern CPU are, 1 in 1 million happen really, really fast, like in matter of seconds usually. and so, this is how you make your program. This is how you make problem really big, really fast, right? So there is this quote, I don't know if that's interesting, but basically there is this saying that say, doing the same thing and expecting different result is pretty much a definition of insanity. And so, if you want to program multi-core CPU, you got to be insane, because this is what's going to happen. So what are the problems you encounter? So you have some usual suspects. Obviously, the language semantic that I've done before multi-cores, and so it's going to bite you back. You have the compiler that's going to do all this kind of optimization for you to make your program faster that are completely correct on a single core and that are completely incorrect on the multi-core. And you have the CPU itself that try to do all kind of stuff to speed up your single-threaded code, and at the same time, the optimization are not visible on the single thread, but they may be visible to other core, and you got to take that into account. Most languages are defined before multi-core, and they do not multi-thread at all, at least not in a safe way, and they do it in an undefined manner. And so what happened, like recently we have been seeing a lot of retrofitting of the semantic you need to handle multi-core CPU in existing languages. So there is some that have been done in C++11. You have like the GSR 133 that have been introduced in Java 1.5 that define volatile in Java and that define it to be sequentially consistent. So you see like some addition, but they are not integrated in the core of the language, and basically that makes your code unsafe by default, and you can make it safe if you do it the right way, right? If you align the stars properly. But nobody is gonna say anything. Nothing is gonna say anything if your program is wrong. The problem is that it's very difficult to change the semantic of existing code, and people really don't like it when you make their code slower, right? So it's not like you can say, well, no, all those read and write, all those optimization we are doing, we're not gonna do them anymore. And so it's gonna be correct for multi-core, right? But everybody is gonna be angry because their program were running fast and now they're running slow, and nobody likes that. So yeah, what Multicore programming language does is that they add new well-defined option. And this is really important for newer programming language to have like a well-defined semantic of what happened to multicore. Like this is a really big problem to solve. There is some solution in the I'm coming into that. Can be made safe by default, rely on the programmer, So the compiler, same thing, does the best to make your stuff as fast as possible, preserve single-threaded semantic. Optimization can be done that are correct single-threaded, that are incorrect multi-threaded, and you gotta disable all those optimization where you are on a multi-core machine, and that's not good, basically. So, yeah. You gotta make everything slow or everything unsafe by default. with existing language, with existing semantic. So the CPU, as I explained, they have all their own cache, and they read and write from that cache. But there is the other CPU that don't see all those read and write, and it can get out of sync pretty badly, depending on the memory model of your CPU. x86 is nice. It's not completely consistent, but it's mostly consistent. But if you go on ARM or MIPS or this kind of architecture, you're going to see a lot of weird stuff if you are not very careful. The problem is that all the data are committed to memory asynchronously, and the core, when they read to memory, they may read some outdated stuff, right, or even some data that are completely corrupted. So they can even, like in the worst case scenario, erase each other's write, right? One write to its cache, another core write to its cache, one commit, the other commit, and only one of the two writes actually exists in memory. That's super bad. So our hardware friend, they made something called cache coherency in CPU. The usual model to explain it is MOSI. This is a simplified model, right? Everything in hardware is much more complicated than whatever people will present you. But this gives you a good general overview of how it works. And so this is a cache coherency protocol. The core exchange cache line, and they have cache line in different state. And by exchanging those cache line and exchanging the state of those cache line, they can ensure that there is at least, they can at least agree on something, right? And things can be made consistent if the programmer wants to. So there is a dedicated bus on the chip for the core to talk to each other and exchange those messages. Well, as I say, it's simple. It's simplistic. Even actual implementation on actual CPU are more complicated, but the general idea are the same, right? And there is no point in digging in too much detail here, because it's going to depend on every single model of CPU. The general idea is always the same. So you basically have 4 states your cache line can be in. And then this is a matrix. So either your cache line is dirty, it means that there is some data in your cache line that are not yet in memory, or your cache line is clean, which means that it's like an actual copy of what is in memory. And you have it in read-write mode, or you have it in read-only mode. And so this is the name of the different state you can have your cache line in. And if you don't have the cache line, then you are in invalid state. So how does that work? If you want to read, this is where it gets a bit tricky. But if you want to read, if you are in every state, basically, except invalid, because you don't have the cache line, you just read from the cache, right? And if you are in invalid, you got to ask the other core, do you have this cache line for me? And if another core have the cache line in own state, they give you a copy and you get it in shared. But otherwise, if they have it in read-write mode, they got to downgrade basically their state to the read-only mode. So only one of the core can have read-write, or multiple core can have read-only, a cache line in read-only. But there is no 2 core that can write in the same cache line at the same time. This is basically what the mechanism try to enforce. And if another core have it in shared state, they don't really own the stuff, so they just won't forward it, and you got to eat memory. This is one of the deficiencies of this model. There is some solution around that, but we won't get into it. So writing is a bit more difficult. If you already have your cache line in the mode where you can write, you just write to the cache line and you make sure that it's in the modified state, because now you have written into the cache line, so it doesn't reflect what is in memory. If you have it in read-only mode, then you got to send an invalidate request to other core that say, I'm taking ownership of this cache line in write mode, so only me can have it. So please, please invalidate this cache line. And if you have it in invalidate, then that's pretty much the same process. You got to get it from memory or from other core that have it. and invalidate in all of the core, and then you can write to it. So only one core can write to a cache line. Only one core can have the right to write in the cache line at the same time. So there is two nice scenarios. If you want to program to perform nicely, you gotta be in one of those two scenarios. Either you have just one core that use the cache line, and you can use it in read and write, and it's gonna be fast, because basically you don't need to mess up with other core. Or you just don't write, and you can share across several cores, and they can have several copies of the same cache line in their cache. So if you know a bit about D, there is like some, should ring a bell, you know. You should see me coming here. So basically what you should not do is sharing and writing. Actually the CPU don't know to do that. So if you do that in your program, what happens is that you get your stuff in thread local and you write to it, and then you share it across the two stuff. You make it basically immutable, and then you invalidate one, you make the other one thread local in the other core, and you write to it. And so if you have like two core writing to the same cache line, it's gonna be super slow. Even if they don't write the same memory, actually, if they write to the same cache line, there is something called false sharing. You can try that in your programming language of choice. You define two variables in a struct, for instance. You have one thread writing to one and another thread writing to the other one. And you will see the same effect. Like, it's going to be super slow because the cache line has to bounce back and forth between the two core. And that's very inefficient. Yeah, so that's slow, and that uses a lot of bandwidth on the bus within the processor, right? So you don't want that. So you gotta keep that as thread local, and if you want to share the data, share it as immutable, and don't share mutable stuff. Or if you do it, expect your performance to not be good, and expect like this is where most of the trouble will come from. Avoid contention. Basically, writing on the same cache line from two threads is going to create contention on the cache line. If you have one variable you want to, if you cannot get around the fact that you have one variable you want to write from several threads, then you can pad this variable. So you make sure that you have no other stuff on that cache line, right? So if, let's say you have a counter, and this counter is going to be shared across several threads, and they want all to increment this counter when they do various action, then you want to have nothing else on the cache line but this counter. So you will create the contention only in this value and not some other value that have nothing to do with it. There is an example of that. If you look in LMAX Disruptor, there is a GitHub repository for that, I think. And they have this class called padded long in Java, and that does just that. Like, that's basically a long that have the same operation as a long, but that had a bunch of padding around it. So if you want to use it in a multi-threaded fashion, then you won't affect performance of unrated stuff. No. If you really want those right on the same cache line, you want sequential consistency, usually, or you're completely insane. So basically, what is sequential consistency? Sequential consistency is basically the operation appear to occur in some sequential order, and this is the same order for all the cores. And it doesn't sound like that big of a deal, but it's get very, very confusing when you do stuff that are not sequentially consistent. It turns out that's better for developer. Like, non-linear time is super confusing, and if you think you can handle it, you are wrong. And if you still think you can handle it, you gotta watch Primer. I don't know if you know that movie. That's a hardcore sci-fi movie made by a mathematician about time travel, and yeah, just watch it. And if you can understand the movie, then you are smarter than me. And smarter than most developers that don't understand nonlinear time. And yeah, you get some extra optimization from various stuff that get into the way, especially from the CPU and the compiler. So you want to make sure that those optimizations are not down in the CPU or in the compiler by inserting memory barrier when you want sequential consistency. So what are those stuff? First thing is like the CPU has a store buffer. So when you store in memory, when you store in memory, maybe you don't have the cache line, right? And you don't want to wait ages for this cache line to come from memory or to be available from another core or whatever, right? You want your program to continue execute on that core. You don't want to wait. So cache line must be acquired. We don't want to stall execution. So you put the store in the buffer. So basically, you put the fact that you want to store that in memory in a buffer, and this buffer will remember it. And when the cache line is available, then the actual store is going to be made. But in the meantime, it's just waiting in the buffer. So that's what I explained. The problem is when you do load, then you don't have the stuff in memory. So when you do load, you get a look into the L1 cache and into the store buffer. So if you remember the graph before, I didn't do a graph for that one because that was getting very spaghetti-like. But basically, you have like an extra pass in parallel to the L1 that go to the store buffer. And if you have a match in the store buffer, you use that. And if you have a match in the L1 and not in the store buffer, you use that. And if you have no match, you go to L2. And you continue, like you just pretend the write happened, right? You just pretend it happened and you just continue your execution. Obviously it didn't happen, so other core won't see it at all. And that's, that's where it gets tricky. Also, you can acquire the cache line in random order, and so you will commit whatever is in your store buffer in random order. And so your write can appear from the outside of your core to be made in completely random order. And other core really don't like that. And when you debug your program, you really don't like that. And you have another stuff, which is the invalidate queue, which is basically the read equivalent, but it's at the bus level. So remember where different core, when they want to write into some cache line, they send an invalidate message to other core. So the other core will invalidate the stuff. And the other core can say, yeah, sure, I invalidate it, but just don't do it right away. They just pretend. They just pretend because they have the cache line here and they still want to continue to use it. And that's actually not a problem for sequential consistency because sequential consistency is about ordering. So as long as you invalidate it later and you do your invalidation in the right order, you're still good. You don't even want to invalidate right away. And you couldn't actually because for the propagation through the cache, right? The invalidation needs you to go through L3, L2, L1, and do the whole propagation of the stuff, right? So it's like tens of cycles, and you don't want to make the other core wait that much longer. So you say, well, yeah, I invalidated, but you just do it later. So what happens is that you can read stuff from your cache that are actually, outdated. Someone else have done a write in there in the meantime. CPU must check its queue to send invalidate or copy of a cache line. Yeah, because if I want a cache line, if I have a cache line, and I want to write into it, I know I own it, but maybe another core sent me an invalidate, right? So I don't want to say, hey, I have this cache line, I'm going to get it into write, please invalidate your stuff. Because for the outside world, you pretended that you invalidated already. So if you are in this kind of situation, right, before sending the message, let's say you go through the invalidate queue and you say, oh, I already invalidate that, right? So I cannot make this request. To make sure everything happens in sequential order in your program, you want to say write barrier. There is many different models, but I'm gonna use it the one as defined in the GSR 133, which is in Java. They are worded differently and with different concepts, but they boil down to the same. So define 4 kinds of write barrier: load, store load, like all the combination. And basically, loads mean that when you do a load, and when you have a load barrier, the load you do before actually happened before than the load you do after. So you know that if you read a value before a load barrier, and then you read another value after the load barrier, you know that this other value is at least as recent as the one before. You cannot read something that is more outdated than what you read before the load. And the other one, just do the same for store load store. And most of them are actually pretty easy to ensure. Like if you want to ensure load, you just have to process your invalidate queue in order. And you don't want to process it out of order. So when you have like a load barrier, then you process what is before, and what is after the load barrier after in the invalidate queue. And you're good, right? And the store is the same for the store buffer. You want all the store that are before the barrier to be committed before you start to commit the one that are after the barrier. That's not a very hard constraint. Actually, x86 ensure that, but there is one that is like super hard to ensure, is the store load. Because you need to basically flush your store buffer, invalid your old queue before you continue processing stuff. And that's something you generally don't want to, like that's a huge, that's a red light, right? You're in a ferry in the city and you stop at the red light and you don't go anywhere anymore before the green. So you don't want that. This is the most expensive barrier, and no mainstream architecture answer it. Basically, this is the only barrier that x86 don't ensure. All other x86 just, do it nicely for you. So this is like on x86 on ARM what kind of instruction you can materialize this barrier with. As you see, this is a no-op on x86 for most of them. x86 is really nice with you when it comes to multicores, except the stored load one, because this is the most expensive one, so you don't want to do it all the time. As you see, ARM, which is probably the other very common architecture, doesn't answer any of it, and you got to add barrier yourself if you want stuff to be sequentially consistent. And otherwise, it's going to be really bad. So we are doomed. We have years of optimization in the hardware, in the compiler, and everything that's completely fired back on us. What your program look like on a multi-core environment is completely incorrect, basically. And this is like completely impossible to bake all of that back. Existing language have terrible semantic for it. They implicit share memory that is writable. Like almost all languages, like either they don't do multi-thread at all, or they just share everything mutable implicitly by default. That's really bad. You have basically no correctness, and the developer, that means you must ensure correctness by itself, by himself, herself, whatever. It gets worse because the standard testing practice just don't work at all. You can pass the test, like, if it's failed one time over a million, you're gonna pass the test a significant amount of time, and it's not gonna fail. And then you run your program on production, and after 1 minute, it's just gonna fail. Because 1 million is just not that big in production, considering the speed of the machine we have right now. So you gotta prove your stuff. And if you read some paper, like computer science paper and stuff, this is something you really don't want to do. Well, maybe you won't. You have different taste, but this is hard. This is hard, and like this is very very detailed work. You have to think about every single detail of your stuff and every possible altering of all the operation you do on several threads, and this get like exponentially difficult as the complexity of whatever you try to prove grows. So that's not very scalable anyway. And failure are completely non-deterministic, so you're gonna fail in prod, you're gonna try to repro, it's not gonna repro, and you're gonna just guess. And this is not a good situation to be in. And that means this is very hard to debug, and this is like impossible to bisect, for instance, to know what I introduced a regression. So like this is the worst stuff that can happen basically to you. So what D does about it? Newer programming language, they must do something about it. they have a memory model that actually handle this pretty nicely. So everything is thread local by default. Global aren't really global. The talk before explained how that works. Basically, all the global are actually thread local. And if you start a new thread, then there is a new global, not global, in that other thread. And data can be shared between threads unless you do it explicitly. So I guess everybody here can understand that, I guess. So yeah, everything is local by default. The compiler can optimize everything that is thread local aggressively like it did before for single-threaded code, because this is thread local. So that's pretty nice, right? You don't need synchronization or any of it. So all the old stuff that the CPU does, that the optimizer does, still works for everything that is thread local, and that's good for us. Except with the main difference with other language that we can prove that it is thread local, so we can prove that it is safe to do so. All information sharing is explicit, so that makes life easier for the compiler, for the developer, for everybody. We also have immutable objects. Immutable can only refer immutable. So you don't have implicit sharing down the road, right? If something is immutable and you share it, and it can have reference to mutable stuff, then implicitly you're going to share mutable state, just because like the two threads are going to dereference pointer in there. And so you're going to have the stuff to be transitive, meaning everything that is referenced by something immutable must be immutable. And immutable stuff can be shared between threads. So once again, like pretty simple stuff. If you have something immutable and you have an indirection in it, whatever goes through the indirection must be immutable as well. You don't need any synchronization for immutable as well. As we saw before, CPU are good at sharing stuff that are mutated. And by definition, because they don't mutate, they don't change, and so you cannot see the change of order. And so that's very nice, and that works very nicely. That composes very well with whatever technology we have right now. There is some optimization you can do based on immutability, because if you load something and you reload it somewhere down the road, you know it haven't changed, so you can assume this is the same value. Even if you cannot prove that there is no load in between that alias, whatever, like, you must assume if the program is correct that the value haven't changed. As far as I know, it's not done right now. Maybe LDC does it? No? No? There is a notation in the LLVM-IR to tell that to the compiler. So that may be worthwhile looking into. And so you have also this stuff called shared that nobody wants to talk about and nobody wants to use because it's horrible mostly, and for good reason, because as we saw, this is what the compiler don't like, this is what the CPU don't like, and this is what you don't like. So if it's horrible, that's a good thing. Yeah. So this is transitive as well, so you don't share stuff that you don't expect to be shared for the exact same reason that immutable is transitive, shared must be transitive. And the compiler must ensure sequential consistency, which means the compiler must add the barrier we saw before. So whatever you update in there appear to other core to be updated in the same order that you actually did the update, right? So you don't see your data structure in some weird state where, I think I've lost, yeah, okay. You don't see your data structure in some weird state where half of it is updated and half of it is outdated. That's nice to have. If you really want to go that road, that's what you want. I don't think DMD does it, actually. I don't think DMD insert the barrier. The specs say it should, though, so it probably should. Your love free code is probably wrong anyway, so just don't put too much hope into this. And then you generally want to avoid it. So it's a nice summary of what your heap should look like, unless you have some bad corruption in there. meaning you've done some system stuff you probably shouldn't have done. But you have like one green heap per thread that can refer either immutable or shared stuff, and shared stuff can reach immutable stuff.
The main advantage of the shared data type is when you do have a race condition or sequential consistency problem, it greatly reduces the amount of code you have to look at to find the problem.
Yes. Yes, that's actually a positive thing. Like, usually, when you have trouble with data races and stuff, you know that you gotta look at some shared stuff or some C stuff. So the current DGC stopped the word mark and sweep. It logs on all allocation and deallocation. At least last time I looked into it, this is what it was doing. It finds the memory pool in log n, so that doesn't make the scan very efficient. It's not precise, not concurrent, not generational, and not parallel. So that's like a basic GC, right? It works, it's nice, but there is like many research and stuff that I've done in the GC world that we probably should import. And one of the problems we have is the API between the runtime and the compiler to talk with the garbage collector is actually fairly limited and limiting sometimes. So if we want a good allocator for D, we want something that is fast at malloc-free kind of use case. We want that is fast at GC kind of use case. You want interior pointer detection, and this is way harder than it seems actually. Because if you have like a pointer to a field on a struct, you don't want to collect the struct, right? And where are you gonna scan this stuff? You have the pointer to the interior of the stuff, and you gotta find, what is the address of the struct actually. And it doesn't sound like a big problem, but that actually put a lot of constraint in the internal data structure you can use for the allocator. You want low fragmentation. For what I explained before, you want to pack data as much as possible to minimize the cache line you use and to minimize the page you use, because both resources, like both cache for both resources, are actually fairly limited. So you want to pack a lot of it. You want to be compliant with system programming. That's also a big one, right? VM languages can do all kinds of tricks. We cannot. And we have good reason to not do them because it allows to do certain things, but it also put constraint or completely disallow some other things. And ideally, it's going to maintain metadata for arrays. So when you allocate an array on a heap in D, you have some metadata with it to know if you can grow it or if you need to reallocate it, for instance, when you append something. You have some of those metadata. And those metadata are actually mutable, even for immutable arrays. Like if you have a string and you append to it, you may not reallocate the string, right, because of those metadata. And you're going to update those metadata. So you don't want to put those metadata with the data, because this is mutable state and the data are going to be immutable. So you probably want the allocator to be able to give you a slot of metadata that you can use in the runtime. I have some work in progress for SDC with that. The idea is to segregate the heap. So you still have a TL heap that stops the word mark and sweep, but just the word here, because it's a thread local heap, the word is just one thread, right? So it's gonna not stop your whole program, it's gonna just stop one thread. And you have an immutable and shared heap. And I'd like to do concurrent collection on that. So I have some reason to do so, I'm gonna explain. You need the right barrier to do concurrent collection. It may seem to be a problem, but it's not gonna be as bad as it seems. So yeah, thread local GC, pretty much what you would expect. This is mostly working. Stupidly, it only scan, but do not collect right now. So it can determine everything that is live and free, but just, keep everything anyway. Because why not? But otherwise, it does pretty much everything. There is this array metadata that is nice to have that it doesn't do it yet, but mostly it's getting there, right? It's pretty good shape. The share heap, So we'd like to have a thread local cache mechanism as tcmalloc and glmalloc do, just to reduce contention because we don't want to run into the lock every single time. And then we have the concurrent collection problem, which is basically I read a reference from memory, right? I put it in a register, let's say. And then I write something else in this memory. And this memory haven't been scanned yet. And then the garbage collector is going to scan this memory and not see the reference I erased. And because of that, I need write barrier. So when I erase this value, I want to make sure that the garbage collector is aware of the old value that were in there. But this is good because you have like no more weird GC pose. You have free concurrency, right? On a mono-threaded program, you can actually see performance increase from this kind of stuff because you have a second thread that is doing part of the job for you. This is typical when you see benchmark of Java and C++ when you have like very allocation intensive stuff with very nested graph of objects. You see usually Java have higher performance, lower efficiency, but higher performance because it can defer part of the workload to another thread. So there is more work done total, but there is like less sequential work done compared to C++. And in this kind of scenario, you see Java outperforming C++, at least from naive implementation, because then you can multi-thread your C++. And you're going to probably crunch Java, but this is extra work. So we require a red barrier, and this is difficult to do IoT. Basically, you have two solutions. You always insert red barrier. VM can do that because they can swap implementation, but we really don't want to do that. So the alternative is to use the MMU. And the problem with the MMU is that it traps everything, and it's extremely slow. By extremely slow, I mean the trapping costs few thousand cycles. It's going to depend on the operating system and the hardware you're on, but you know, it's in the few thousand cycles, so that's pretty expensive. But it's not that bad because, well, it's not that bad because everything you share is going to be mostly immutable, so you don't write to it, basically. But you have new allocation. So what you do with new allocation, you can allocate while you collect, right? So all those new allocation, you just consider live, and you're going to write to them, but you don't care. They are live, and you're going to not scan them and collect them. And you want to protect unscanned memory. This is done in ML languages. And they do it, and they have like very good performance out of it. So I am hopeful that I can get very good performance out of that in D. Write in memory, in shared memory, I mean, is immutable initialization, so just after free. So this is not in what you scan. This is, you know, so this is not going to be protected. And you have some shared write. And if you use shared, you know, you see what's coming. So. My point of this is like you probably deserve it. But you know, I guess you know MMU is going to work nicely for that. There is another problem you run into is sometimes you have what I would call implicit sharing. You have three main situations where you're going to have implicit sharing. The first one is delegate. That can have a pointer to a context that contains mutable state. And right now, delegate don't propagate type qualifier for this context pointer. And this requires actually a way to qualify the context of the delegate, which we currently don't have. There is a deep about it. That's important. But this one will not handle. This is probably a language bug, I'd say. You have an exception. So when a thread terminates with an exception, it's going to bubble in whatever other thread join that thread, right? And it's going to create sharing there. It doesn't really matter because this is only when the thread terminates. The tricky one is pure function, as in strongly pure function. And you allocate some stuff in the pure function. It appears thread local within the function, but outside you want to promote it to immutable because you know you just have one reference to it, so you can do it. Those merging std allocator needs to handle that, and right now there is no good stuff in std allocator to handle that. Except that, like actually, I'm fairly positively surprised by how it's coming along. But this is this is one of the dark points. So you need to do heap merging. Basically, you have one heap and another heap, and you make one big heap with the two. The tricky one is the pure function. So you want to create a new heap, set it as the new default thread local, and then when the function returns, you merge that heap into immutable. Well, I want to do some optimization. Immutable is naturally generational, meaning you don't modify the old object to put reference to newer object in immutable. I have no way to take advantage of this characteristic in the ahead of time compiled language. So if you have some idea, you can tell me. But that would be that's a nice property. We don't exploit it at all, and maybe we should. When a reference does not escape, the compiler should definitively see that and add an explicit free instead of letting the garbage collector do its job. And when you have a pair of allocation free, you promote on the stack if you can, if you know the size. So this kind of code really should not allocate once the optimizer is passed on. Because this function that returns an array is going to be inline, and then you see that this doesn't escape, and you should really be able to do this kind of stuff, and the optimizer remove the allocation. You should be able to do this kind of stuff as well. I guess I have some other stuff, but I guess I covered as much. We're running out of time, so I'm gonna take question now. It's a good time, no?
So when you get something, whatever situation, something is implicitly cast to immutable, doesn't that mean that you're
implicit cast to mutable?
To immutable.
Okay.
So
yeah.
like the return
when you
from a pure
return
function.
From pure function. Yeah.
Doesn't that need a write barrier then at the point when it becomes immutable to make sure that you've actually
when you
published,
merge the heap,
right?
when you merge the heap, you're gonna need a barrier. Yeah.
But even now, don't we need it? Never mind merging heaps, right? Don't we need a write barrier there?
Even now?
How it works now?
Well, no, because you don't really need a write barrier until you actually share the stuff.
Yeah, but
you're gonna need it in this situation, because when you want to merge the heap, you want the code that merged the two heap to see something consistent. So you want a write barrier in there. But in what we do right now, you don't need a write barrier in there. You need the write barrier when you are gonna actually pass the immutable reference to some other thread.
Oh, yeah.